Okay, well, it's my great pleasure to introduce Ciprian Chelba, who's coming back to us to give us the wisdom of what? I mean, I believe he got his PhD in 2000. Is this true?
Yeah, January.
It's just incredible that how time flies. He came to us maybe in '94.
Yeah, it was the year of the World Cup.
Yeah, the year of the World Cup.
Yeah,
Yes.
the way I remember it is
94.
we graduated the year I bought my car.
I see. Okay, and I believe in '95 you worked at the workshop, did you?
96.
96 in one of the original language modeling groups. And
In
since
fact, his thesis idea comes from that workshop.
Right.
At least it's German.
and then from here he went to Microsoft, and it looked for a while that he likes it, but about a year ago he switched to Google. So anyway, I'm giving you Ciprian Chelba.
Yeah, thanks, Fred.
To all the students, if you work really hard and do well, you could be like this.
Yes, he certainly did well. Okay.
So far.
Yeah, well, it's too early to tell, of course.
My name is Ciprian Chelba, and what I'm going to be talking about is spoken document retrieval and browsing. This is mainly work I've done at Microsoft Research, and I'm hoping that I'm going to be able to, I'm pretty sure I'm going to be able to work on it at Google too. So, let's see how this works. Right. This is a quick outline of the talk. First, why do this? Then I'm going to review a little bit of the text-based technology that is out there, and then I'm going to try to see. Well, first, it's fair to actually look at what people in the TREC spoken document retrieval evaluations did as well. So we're going to have a few slides on that, and then I'm just going to present a slightly improved version that we have using speech recognition analysis, and I'll motivate that and give some results there. And finally, if I have time, I'd like to show you more of the demo that was playing when you walked in, and hopefully we'll have time for that. In the past 10 years or so, there's been a lot more video and speech type material available on the web. And I think right now we stand at the point where we have the latest figure I heard is 60% of IP traffic being video material. And it's heavy, but people do this a lot. This trend, there's nothing really stopping it. If anything, it will accelerate, because the cost of saving such material, producing such material, and exchanging it, over high bandwidth connections, keeps dropping. So this is actually in full swing, and you see anything from there's broadcast news.
What do you mean we have 60%? That means on the web there is 60% of traffic.
Traffic, yeah. If you measure traffic on the web, 60% of it is video.
Is video.
It's heavy. There's a lot of stuff to send. It's not text, but at the same time, it's a telling figure. I think 60% was the last number I found, but 50% is for sure. In that ballpark. I don't need to explain broadcast news. Podcasting. How many people know about podcasting? Okay. Yeah. Time shifting of audio content. Sometimes people mistake podcasting like the medium, the broadcasting medium. That is, I download stuff onto my PDA and listen to it, to the actual content and activity that podcasters do, the producers of this type of content, which is to record material and post it on the web. So these are two different things that sometimes are used interchangeably. Here we talk more about the type of content rather than the broadcasting medium. And of course, there's
So podcasting is availability. In other words, I can have it and I can make it run, but
Well, so the scenario is one where you have a little PDA. I don't have it with me. I mean, it's in my bag, but it's something of this size. And you hook it up to your computer every night, and you have some list of sites that get scanned and downloaded. And then when you go exercise in the morning, or when you take the train, or so on, instead of listening to, I don't know, friendly talk, you would just listen to stuff that you care about. And I don't know how much of this people really do, but it's definitely something that is very hyped in the media, and it's becoming increasingly popular. There's a lot of these gadgets around. Apple is doing quite well. So it's from the iPod. That's where it comes from. And then academic lectures, you know, I'm being recorded as I speak, right? There's a lot of this type of material around. And in Microsoft Research, we had 10 years of it, and there were at least 4 or 5 hours recorded every week, different speakers. And over 10 years, you know, that amounts to, you know, we're talking at least 500 hours of speech. But more importantly, you lose the collective knowledge of what's in there. So somebody who gets hired now into Microsoft Research has no idea when so-and-so came and talked about something that might be quite relevant to what he wants to do. And there's really no good way of finding out about it. You can search for the title, you can search for the name of the guy, some abstract, if that was saved with the talk, but that's about it. So it's a little unfair to this really rich media, because you know, there's a reason you guys are in this room. And I don't deliver this over the web. And you know, it's the same for this type of media. So this is just to motivate why we would actually want to do an automatic, you know, enable people to search this type of data and content. And I'm looking here at a particular paradigm. I'm looking at keyword-driven spoken document retrieval, which is the same idea that, you know, it's like what you do when you search the web, right? You go and type in a few keywords in a box, and you get relevant documents, and then you have some good way of telling what they're about. There are the snippets there, and you can actually quickly go there and look at the snippet in context and see, is this what I care about or not? And we would like to be able to enable the same kind of experience for this type of content, spoken and you know, video content. And it's important to realize that it's not just a search problem. There's a lot about browsing the documents as well, right? So we want to be able to search and retrieve them, but then we also want to be able to quickly scan, which is actually a very time-consuming task. It's much different than what you do on text. On text, in a few seconds, you sort of read a few sentences or, you know, a paragraph, and you're sort of done. You get the feeling. We're very good at that. Our natural language faculty is amazing. When it comes to consuming speech and video content, it's a linear medium. You can't skip. You start where you start, and then you have to listen to the end. It's like listening to a boring voicemail, and that's just all you can do with it. That limits consumption. You can't browse the hits quite as efficiently as you do it on text. So you're going to need to do things a little differently, and we just don't know how. But it's very important to quickly find the segments and be able to tell which are the documents that we care about. So what could we do? I mean, what information do we have at our disposal to enable such an experience? And of course, the first candidate is, well, we want to transcribe the speech, right? There's a lot in the words that will help us search. But although the rest of the talk is going to be focusing on that, I want to make sure that you understand that there's other information sources that are likely to be very, very good predictors and help us in this search. And you know, you do get a text summary that some people enter for given lectures or even for video posted on the web. You don't know how reliable it is, but you typically have some limited amount of text content associated with it. You can start thinking of, well, who is the speaker? If there's more than one speaker, could we align the speakers against the material and only browse by speaker, for example. I want to know when Fred spoke at the beginning of this talk, because he definitely probably has something to say about what I'm going to talk. It's, you know, that type of stuff. You get slides. I have slides, and they're going to be available online, and you compare them with the material and say, well, you know, I consider choosing this. I sent, I remember I sent Keith, right? I sent you an abstract, title, everything. So that's going to be there on the website. You can mine for it. Probably more interesting stuff, just as you do. People here, I assume, are familiar with PageRank. Yeah, just a few.
What?
PageRank. So in World Wide Web, you know, in web search, there's the concept of the IR score of a document, which is I give you a query, you tell me how relevant the document is to that query. But there's also an a priori relevance score that is independent of any query, and it comes from the graph connectivity. And to explain it best to a technically savvy audience like you guys, it is the stationary distribution on the Markov chain. If you look at the graph as the Markov chain, and the transitions are the links, well, there's a stationary distribution there under some smoothing assumptions, which you make. So that tells you how important each page is in absence of any query. That's PageRank. And we can propagate PageRank from those sites to the videos if there's links to them. Like, for example, if this talk is interesting, somebody will link to it. From the CLSP website, it's going to be linked, hopefully, I don't know. It might be linked from Google Video, if I decide to do so, or upload the talk there, who knows. But there might be links from important websites that point to a given video. Well, you want to use that information. I can guarantee it's going to be very, very important. There's going to be text on each of these links. It's called anchor text, which describes, well, where is that link going to take me? Again, very important feature. So don't think that, and of course, there's collaborative filtering. You can keep track of who watched what, right? So if I'm a user that goes to YouTube or Google Video, you probably see, well, you know, whenever I went there, I watched so-and-so videos, right? So you have a list of things that I've watched. And then here's a new guy who watches more or less the same stuff. Well, you can recommend him. Well, you know, you may want to take a look at this too. It might be interesting for you. Yes, Jason?
Just a quick question on collaborative filtering. So I know that if I happen to be logged into my Google account, which I am more and more often now because
very good, yeah.
I don't bother logging out, then you know what I clicked on. And
I'm not sure. I'm not
yeah.
sure whether we know or not.
In principle, you know. I mean, you could
something may get logged. It also, there's a privacy statement there, and you could accept that certain things are logged or not when you go into your Google account.
Yeah.
I don't know if you checked that or not. There's a check bar.
I don't remember actually, but the.
So then you don't. You have.
Yeah, but get to the point.
It's not
because
so
it's not checked in by default.
So my question is, how much of the traffic at Google can be linked to a user, so that you can do collaborative filtering?
How much of the traffic at Google can be linked to a user?
Sure. If you take a random user clicking on a random link or video, or issuing a random search, how often do you know who it is so that you can make user-specific?
You never know who that user is.
Well, you do.
You have some number associated with that guy, and
you're using cookies all the time.
I really don't know how many of the users are actually, they have Google accounts. If they don't have a Google account, you don't have any information on them.
You don't log them by cookie?
Not that I know. I don't know. But is that tied to a user? That's tied to a browser, no?
Yeah.
It's tied to a session, a browsing session.
A browsing session, not even a browser.
Well, there you go.
So
you can have a cookie that lasts longer than once.
I honestly don't know. I mean, this is a little secondary.
Okay, sorry.
But really,
just trying to squeeze information in.
right. I don't know the answer to these questions. Really, privacy is very important to Google, and you, as an employee there, you can't find out anything from the logs that is not aggregated to a level that is approved by certain people. It's probably the first business that really depends on the trust of its users. It is a business imperative for Google that the users trust Google, which is very important. Anyhow, so right. So, okay, well, we'd like to do that. But when it comes to transcribing speech and all this, does it really make sense? I mean, do we, why isn't there some other way? If we know speech doesn't work that well, is it going to add a lot of value? So there are a few scenarios where you really don't have much else. And if you look at lectures or large amounts of data, if you have a lot of data, it's just impractical to pay the upfront money that it would take to transcribe all that. It's somehow TV is probably the likeliest candidate in anybody's mind that we should apply this to TV, but somehow that's not so interesting for several reasons. And one of them is that there's an FCC regulation that says everything that is broadcast starting with January 2006 on major TV stations needs to be closed caption. So at that point, you really don't need to do speech recognition. Maybe you need to align it to be able to browse and so on. But and then broadcast news, as I'll show later, is more or less easy in this space. But there's a lot of other content that is not easy to transcribe by hand, primarily because of cost. If you look at the cost, it's about $100 per hour, and while that might seem a lot of money, if you're inviting George Bush for a half-hour interview, and if you already spent $100,000 on that, spending $100 to just transcribe it to make it available to everybody is not a big deal. So it might happen there, but if you're a podcaster and you spend $300 on everything that you have to do podcasting, well, you're not going to spend $100 on every hour that you're going to put out there. If you're an academic organization like here, again, money is important. So then there's the privacy issue. Sometimes if you're a business, you have customer call sessions, people call with problems. Well, that's not something you want to just let out in the world, for sure. You want to keep that in-house, analyze it, make the best out of it. Same goes for me as a private person. I have my voicemails. I may have VoIP chats. Those are not things that are...
What's a VoIP chat?
Well, voice over IP, like if you use Skype or...
I've used Skype.
Okay.
I'm not
So
using it, but I have used
Yahoo, Messenger, Google
Yeah.
Talk.
And that's called VoIP?
Voice over IP. I think
I
it's an established acronym. I don't know.
Okay.
Does that make sense to everybody? Yeah. I just used it without knowing.
that's fine.
Yeah. Okay. So there is this, there's these dimensions along which you may look at the given project and say, well, do I want to do indexing and search using automatic speech recognition or not? And there's considerations that need to be taken into account. Okay, so just to establish some notation, we're going to look at document collection 1 through n. What I call large is anything above 10,000, a million documents. And we're looking at, longish things, videos, lectures. If you have voicemails, VoIP chats, and you have less than, 10,000 or less, I would think that's a smallish collection of documents. The query is a list of words. They come in a very large vocabulary, and typically they're not just a bag of words. They're not just a set of words. There is inherent structure in the query, whether you realize it or not. And you've been using it in Google for sure, if you use Google as your search engine. There's other different ways of expressing queries, and you can start using query operators. There's ways of putting structure into this query. So we're going to just look at queries that, keyword search. As I was mentioning, you can start looking at other query languages. For example, you can just take a waveform and just speak my query, and maybe you can find matches in speech that way without doing speech recognition. Again, the collaborative filtering doesn't really look into the content. It just looks at how people treat it. You can think of the early days of web search when there were ontologies for web pages and so on. Maybe you can try doing something like that. As far as standard text retrieval algorithms, it's good to review those very quickly. You probably, how many people here have seen TF-IDF before? Okay, everybody. So, very simple. What happens there? You just take each word in the vocabulary and you somehow compute a co-occurrence matrix, which ends up being pretty big, both on the vocabulary side and on the document side. And then you use the term frequency in a given document as the, how likely is, how relevant is this document to a given query. And I have this second term, which is the inverse document frequency, which tells me how telling is the word in the query for being able to disambiguate between documents. And it's related to the entropy of the distribution of documents given a query word. People have been using basically that. Belagarda, I think, uses that, the conditional distribution of the document collection given a certain query word instead of IDF, and gets good results that way. But there are some problems with TF-IDF, and it's a hit or miss model. And if you get the queries, the query words in the document, you're going to get the document. If you don't, well, you don't. And here's an example where clearly we have a relevant document. Its code brand is the most treasured asset of the soft drinks maker. And if you type in Coca-Cola, you're not going to get this document, right? You cannot do phrase search. There's no way that is built into TF-IDF to let you search for Coca-Cola as a phrase. You need to do some post-processing, and that's actually a symptom of a bigger problem. You are ignoring word order and proximity information. And one example here is, let's say that you want to query for object-oriented programming. That's your query. And you get one document that says the object-oriented paradigm makes programming a joy. Clearly relevant, I would say. I don't need to read more. The second document says TV network programming transforms the viewer in an object and it is oriented towards, right? You have exactly the same counts, and yet I can immediately tell that the second document is not something I would like to look at. And the problem here is clearly a modeling problem. We want to be able to come up with a better scoring of the document given the query. So another model is along the lines of probabilistic language models, statistical language models. Steve Robertson, I think, was the first one to put it out there. Let's say that you do have somehow probability on documents and queries. And then you say, well, really, what is it that I want? There's this idea of mutual information in the point-wise sense, which is a little bit of a hack, but I can calculate this quantity, right? And it sort of looks like mutual information, except that you don't sum over all documents and queries, right? And you can't, because you actually care about one given document and one given query. And if you take out the query-independent term, you end up with the posterior probability of the query given the document. And you're going to say, well, so clearly what I need here is a language model that is going to predict my query given the document. So I'm going to build such language models and for each document. And then I'm going to predict the query from that as a sequence of words. And I now take word order into account. You can imagine how the n-grams, if they overlap, you get higher scores, higher probabilities. You're going to start modeling query n-grams, but probably more general proximity features are hard unless you put them into your language models. Like skips, a few words are not really modeled right away. Order is, left to right, I guess, caching. But it becomes very expensive to store. I think that's probably the big killer here. If you think about it, as you slide the n-gram window over every single word in your training data, you're going to store that 3 times if it's a trigram. That's a lot, especially when you work at big scale. So people started looking into other models, and Brin and Page, before taking Google into business, came up with this ad hoc scoring method, and it was very commonsensical. They said, well, why don't we think of a hit as being the occurrence of some query word in a given document? And I want to store a few things for each hit. I want to store context, and by context I mean where does it happen? Is it in the title? Is it in the body? Is it in what font? If it's in big font, it's probably an important thing. If it happens on anchor text, as I was pointing, to another document, that's probably a good keyword describing that document, and so on, right? So we have different types of context, and we want to sort of keep track of those. And there was also the proximity issue, right? But yeah, I don't want to get to the TF-IDF case where I forget about proximity. So I'm going to also store the position of each word in my document as an integer, right? So that's a hit. It's basically a word together with an integer describing the position in the document and some other context information in which that word happens in the document. So that's the sufficient statistics I keep for each document. And then I can do relevance scoring for each document using some of the proximity information that I like, namely, are these words close to each other, even adjacent, or within a window of 3 words, within a window of 10 words, within a window of 10,000 words, right? If I have such a long document. I know the order. Then I can also ask, well, was this in the title? Was it in anchor text? And so on. So you pretty much build a set of features, just like you would do in regular, I guess people have played a lot with low linear models and such, Maxent and so on. So you can imagine a collection of features like that. And then you need to score a document using those features. And the only question remaining is the weights. And for that, well, there's no good answer. And that's why I call it a little ad hoc, and yet extremely effective. So people, Google in particular, found that to be very useful. One more point before going into spoken document retrieval, very important. If you work on large collections of documents, you cannot afford to linearly scan each document at query time. So the best example I can think about it is, think the inverted index at the back of a book. If you're looking for a certain keyword, and you're luckily in the scenario where it was indexed by the author, it tells you exactly which page to go, right? And now contrast that to searching for, I don't know, mutual information in the Thomas and Cover book, page by page. Well, it's going to be quite a lot longer, right? So that's the inverted index, and you want an inverted index whenever you work on large collections of documents. And it may seem like a simple thing, but it's not obvious to everybody. So I wanted to have it here written down. And pretty much all these methods are amenable to some form of indexing. And TF-IDF is obvious. For language modeling, you need to store or a given n-gram model for every document. That's a lot. So I think it's prohibitive there. As far as Google, you can do it. And I just told you what the inverted index should contain there. How do we evaluate? Let's say that, you want to do information retrieval work, and you want to evaluate your algorithms. So what people in the Trek community are doing is, there's a package out of NIST, and you need to have binary relevance judgments for each document query pair, right? So I have a query. I have a list of documents from my collection. I mean, we can conceptualize that we have all the documents in the collection, and then I put a 0-1 bit next to it, relevant, irrelevant. That's all I get. There's no ranking on the reference side. It's just a set of documents. And then I come with the result of my search engine, and this one is ranked. And there, I start going down the list of ranked results, and I measure precision and recall as I go down that list, right? And I put a dot every time I hit certain recall points, like 10%, 20%, 30%, and so on. So typically, you're going to see a curve of this type. As you go down the list of documents, you get more and more of the original set of relevant documents, but your precision goes down, right? So all the curves are going to look of this type. Well, we have to average twice to get mean average precision, right? So we do one average here, saying I want the area under this curve, which is typical for ROC curves, and then I have to average again over all queries, right? Because this was for just one query. And that's what people call mean average precision. There's a related metric called R precision, which says, oh, why don't I just look, I know I have 10 relevant documents, why don't I just take the top 10 and see how many of those are actually relevant in my ranked list, right? That's the R precision, and it's R precision as opposed to precision at 10 because R varies by the number of relevant documents for each given query, right? And you can do the other standard things, precision recall and precision at 10 or N. So, well, what if you want to do speech, spoken document retrieval? I think that one major sort of different way of evaluating there, which does not need human in the loop to sort of do the relevance annotations and all that, is to take a different point of view and say, well, I'm not in a perfect world. I can't recognize speech 100% accurate, and I'd like to get there, or at least come up with a system that gets as close to that. So my view was different. I said, well, I just want to match what I can do on text with current state-of-the-art text retrieval algorithms. So assume I have the transcription for my document collection. I take that, index it with your favorite text retrieval algorithm, and run a bunch of queries, which I still don't know how to get, but assume you have a bunch of queries, run that through that text retrieval engine, and you get reference lists. And well, they're also ranked, but for now, map the track eval package does not use that ranking. And that's how I'm going to get my relevant documents. And then the question is going to be, how close can I get to that using imperfect speech recognition technology? That's a different way of evaluating spoken document retrieval, which leaves out the humans, leaves out the thorny issues of, well, is this truly relevant or not, and so on. And you can turn it around much faster. All you need is a few queries, and I asked a few friends to play with that text-based index. They gave me about 100-some queries, which is roughly the type of query sets that people in the track community have been using, because it's very hard, it's very expensive to annotate. Because for each query, you need to look at a lot of documents to decide are they relevant or not. So this is how we're going to evaluate. And I like to point out clearly that we ignore the relevance, the ranking on the reference side. And this is just because I didn't want to change the evaluation metric at the same time. I want to use track eval, and I think that we should actually look at how we replicate that ranking too, but that's not what we did in this work.
I think I got a little lost in that. So you're saying that you have a spoken document collection. Let's say for argument's sake you have reference transcriptions for every document, so that you could run a text-based query,
Right.
a text-based search. And then you get a few queries and you run your text-based engine on it. And for each query you get a ranked list.
Yes.
How do you convert that into a relevance judgment file?
No, that's it.
That's
the
that ranked
relevance
list
judgment.
is, and it's for the top 100 of the thing or the top 1,000?
No, all of them, however many there are.
Oh, but what if your text IR system returned the whole collection just ranked?
Well, hopefully it doesn't do that, right? But you're right. That's why we should look at the ranking.
Okay.
I agree.
So for example, you might say I'll do a Boolean search where if the keywords are in there, then it's in, otherwise it's out, and then you'll get a subset of the collection.
So far, everybody does that.
Okay.
That's something that I left out because I don't have time. But there was that hit or miss problem with TF-IDF.
Right.
The reality is, I think, that whenever you try to correct that, like use LSA or fancy smoothing techniques that would retrieve documents that don't have those words in them, I think there you're facing a trade-off between our language faculty, which gets a little confused. Why is it that I'm getting this? And how well that algorithm performs. So if you really give me relevant documents, I'm going to be happy. But we know that these techniques are imperfect. You start giving me documents that have no connection with my query. And it actually impairs my natural language faculty. When you give me just the hits, and I look at the documents, I immediately see other words there, and I know how to steer my query. So I'm more effective, I'm more in control that way than if you put noise in the loop, right? Because it's not just a one-time interaction with the search engine. Usually you refine your query, and so that feedback loop gets destroyed by such a...
No, I'm not getting into the philosophical arguments about what it is, but I'm just trying to understand your evaluation paradigm. So the evaluation paradigm says run a text-based engine on using that query, and whatever documents come back from it, they're all deemed relevant.
Yes,
That's it.
that's how it works. And it worked so well here because we actually had the TF-IDF baseline. There was nothing else that we could use.
Okay.
And to make it even more specific, every document that contains all the words in the query is deemed relevant.
Yeah.
Every document that does not contain at least one word in the query is irrelevant.
Right. And the
So
rest-
there's no more TF-IDF at all. It's just simple set matching. And it's a big problem, I think, as far as, how well are we? We might be actually doing better than we think we are. If we look at rank lists and so on, it might not be that bad.
So the spoken documents came from the track database.
No, we'll get to that.
Yeah.
So here comes a little review of the track evaluation, and I have it here just for completeness sake. I want to sort of make sure you understand what has been done there. How many people here are familiar with that space? Very few. Okay, very few slides. So there was part of the track evaluations. There was a spoken document retrieval track, just as there's a video and image track. It ran for 4 years, between 97 and 2000, track 6 through track 9. And with the years, increasingly, there was more and more data being annotated. The focus was on broadcast news data. By the end, there were 22,000 stories from about 500 hours of audio. So that was a good sized collection. And the conclusion there was that even high SRR rates produced very good document retrieval performance. And there were a few major contributions that were specific to the spoken document space. People started using n-best lists as opposed to one-best, and they started looking at query expansion, see how that helps retrieval along these lines that we were discussing. Also on the document side, you can do expansion on either side of the collection. The bottom line was it ended up being a success story. Things worked out, and the ASR errors didn't seem to hurt performance much. And here are a few reasons. The content words are often repeated. There was another analysis here showing that you have semantic.
How bad were the rates, the error rates?
Well, on broadcast news, so here is what.
Oh, but it's broadcast news, so it's
So in
pretty
broadcast
good.
news, we have, in many ways, it's a best case scenario for this problem, right? Because it's primarily prepared speech read by professional speakers. The spontaneous speech artifacts are not there. Language usage is similar to written material, so our recognizers do well when we train them on written material. You can get a lot of data from the web, new vocabulary items, and so on. So you end up with state-of-the-art recognizers that have error rates, 10 to 15%. And the surprising fact is, if you go and measure the closed captioning word error rate, you're in the same range. These are people who basically type it very fast, right? You're in the range of about 10% error rate. So that was what was used as reference, because nobody sat down to transcribe 22,000 documents, right? So then you have a reference which is at about 10%. You have the speech recognition output, which is at about 10%, and you're comparing retrieval performance on those, and they end up being quite similar, right? Also, the queries were a little peculiar. I looked at some of the queries, and they're very long. In the sense, they're more of a stated problem. Like, for example, why is the imprisonment rate higher in the US than in Europe? Right? That's a good query, that's a good question, but that's not how I would use such an engine. I don't think I would ask this question just like that. One thing that is missing when you look at that is the fact that if you look at the standard searches that we do using keywords, you tend to use highly discriminative words, right? You want words that are not going to give you back the entire web. You don't want to type in the, it's useless, right? So you want words that help you find what you want, and those are the infrequent words. So the keywords are going to be at the tail of the distribution. If you rank all the words in the vocabulary, you have the head, which is the most frequent ones. Well, that's not really the good keywords. The good keywords are closer in the tail, mid and the tail. And that's not how you build a speech recognition vocabulary. You take the head of the distribution there. So we really don't, I think that we don't have a good handle for what truly is the query out of vocabulary rate when you look at speech recognition. Like, how many words in regular queries are not in the standard speech recognition vocabulary, what is the rate there? In our experiments, it was quite high. I'm going to get to that. The other thing for broadcast news, of course, as I mentioned, is a lot of it is closed caption. So it's uninteresting for that reason. There's a good, this may sound a little off the wall. So let's say that we're going to Mars, right? And the question is, what clothes are you going to take with you, right? And you go to your favorite search engine, and you find something like this. Well, the average recorded temperature on Mars is about minus 63 Celsius. Okay, so you need something that will shift the temperature by 63 degrees roughly, 90 degrees or so. But is that the whole story really? Is that enough? Are you going to you build a costume like that, and you go to Mars? So I guess you're sensible enough to say no way, right? I might do that if I go to Seattle because I know that the temperature on Earth varies by 5-10 degrees during the day, but I'm not going to do that on Mars. And in fact, well, the maximum temperature is about 20 Celsius, but the minimum is minus 140 Celsius, right? So something that just shifts your body temperature a little bit is not going to do it. And I think the point I'm trying to make here is that something that physicists know. When you give a measurement, you never say, "Here is the length of this," right? I'm building a car. The length of the drive axle needs to be 1.5 meters. There's always a tolerance for that, and that's why German cars are probably better than Romanian cars. Romanians never managed to get below 1 millimeter in precision. And I remember asking a guy there, and like, well, why things don't get built here? It's like, we can't go below 1 millimeter tolerance. It's just not practical. You can't do it. So we can't build stuff. So I'm asking, are we in the same
Why isn't it practical? I don't understand it.
Well, if you get a
you
drive axle that is 1.55 and then you get another one which is 1.47, it doesn't go well.
No, but why isn't it practical to develop a technology which can do it?
Well, the point is you want to control the variance. That's I think what I'm trying to say here.
Okay, I am just saying that the Romanians might be able to sell cars if they could overcome this.
Yeah, they do. In fact, they do, but they only sell it themselves. It's they're just not as good. And if you want to build something else, you really can't. Like printers, it won't work. Or watches.
Romanian watches have low mean average precision.
I don't think there is a Romanian watch, honestly. I don't think there is. We can check on that, but so coming back to where we are we in the same situation where you start building black boxes? I have a black box that does speech recognition. I have a black box that does information retrieval, and I'm putting those two together. That's what happened in Trek. And if you look at, I just took the top 20 substitutions ranked by frequency, broadcast news versus MIT lectures. So this is the same recognizer, except that this is a different test set. The original recognizer was a broadcast news recognizer operating at some 20% error rate, reasonably good. And you see the errors. There's nothing consequential from a search point of view. I mean, it doesn't matter. These errors won't hurt my search performance, right? So Trek was indeed a success. But if you try to use that for doing MIT retrieval, right? Well, you have Lisp being mistaken for a list. Well, that's not good. The lecture talks about square root, mean square root, I think. Well, then you're just not going to get it. Square is substituting for all sort of other things. So the errors are quite different, and word error rate is not telling us the entire story here.
Excuse me, this is a Microsoft recognizer here.
No, it's a generic broadcast news recognizer.
No, but I mean, Erin, these are the MIT lectures, right?
Yeah,
Yeah. So he seems to have a recognizer for it.
as opposed to what MIT has.
Right.
No, but anybody who has a recognizer can.
No, but
Use it on the MIT
we
lectures.
thought that ours would not be trained for this.
Ours wasn't trained either.
This is a broadcast.
This is
Oh,
a
this is-
mismatch.
The point is it doesn't work.
As soon as you go off the beaten path, that variance hurts you. What I was telling you about, yeah, you tell me the word there is 20% on broadcast news, but if you go to Mars,
Yes, yes.
I don't know, iCampus, all of a sudden, whoop, I don't know, it could be anywhere between 45 and 60% error rate.
Yes,
Right? So can you build anything with that? Coming back to the Romanian watches, right? We need to make sure that we at least provision for that. And here is the problem that I wanted to solve. I wanted to say, well, can we build tolerance to this kind of errors in our system? So instead of looking at speech recognition and IR as black boxes, I'd like to make sure I use the richer information that the recognizer gives me. And in this case, I have, you know, speech recognition lattices. And before we get there, that's how I'm going to handle this. These are the problems that I saw, you know, running a broadcast news system on iCampus. I think 0 to 15% across the board, across all the niches that I'm going to see on the web, it would be perfect. If I could get 25%, but I know that it's going to be 25% on all of them, I'm going to be very happy. I don't need to be below 10%, like switchboard or broadcast news. I just want reliable performance on every single niche that I will bump into. Speech recorded in any conditions, over any channel, any domain, and so on. So that's something that I would like to aim for. And of course, there's the out-of-vocabulary problem that I mentioned. And for the MIT data, we saw that, you know, we had about 5 to 50, it was actually 10% query out-of-vocabulary rate. So that means if you take a query of about 2 words, you end up with 1 in 5 queries that contains 1 out-of-vocabulary word. That's a lot. 20% of the queries contain at least 1 out-of-vocabulary word. So coming back to that variance control problem, well, so when people give you just the one best sequence from a recognizer, that's just really very little information. And it may be a lot of information if that recognizer is switchboard and tested on switchboard, because you sort of know how things go, and you know that, you know, on switchboard I'm going to get about 25% error rate, and I know that 2% difference in word error rate is actually a lot. It's a significant difference. So it's not going to be, you know, that far off. But when you take that same recognizer and run it on some other speech, you don't know. You don't know what's going to happen. And I think the recognizer offers a lot more than that. We have a probability distribution for what the word sequence is given the acoustics. We can actually do a little more than just blindly take that word sequence, not knowing which words are wrong, what is my confidence in each of them, and so on, right? So I'm going to try to do that for spoken document retrieval, and to just show that the lattice contains paths with. There's a lot more information in the lattice. If you just look at the word error rate in lattices, you can cut it to half. You can find a path that has half of the error rates that the one best path has on the iCampus data. That's
Are
not
those,
clear.
are those two numbers reversed?
They are. Yeah. So these are, no, actually, no, this is accuracy. Because the error rate is 45%. So, yeah, so the accuracy in the one best is, no, that's not right. No, these are word error rates and they're reversed, you're right. The problem is when you start thinking of using lattices, and you would like to use something like the ad hoc relevance ranking algorithms that I mentioned, you would like to be able to retain word proximity, engrams if possible, and you want to be able to count these things. And it's no longer obvious how you're going to do that, and that's what we looked at here.
Just back up a second. So I think I know what the thing is. Here you're using a dictation engine. So the error rate went up from 45 to 55 because these are probably a bit more spontaneous.
Compared to the previous slide? Yeah, that was broadcast news. Right. This is the Microsoft dictation engine.
Right, so that's why the error rate was 55 on the one that's.
They're not comparable.
Yeah.
I mean, I'm sorry. I mean, for you guys, 5% is a big deal. We're looking at much bigger changes here than just 5%. So what would you do with lattices? Well, I mean, I think one good approach is, I know that there's all this wealth of algorithms knowledge that deal with text, right? And they've got it down, it works well. How can I sort of make speech fit, shoehorn it into that type of a framework? So one simple way would be to, if we could take a lattice and transform it into something like this. And because I want to retain the probability distribution that I have in the original lattice, I won't throw away, that. But at the same time, I would like sequential information. I would like, where it happens to the left of this other word. So I would like that type of thing that I have for text. So one thing we could do here is to combine a list of what I call soft hits. And if you take all the paths in the lattice, each of them coming with the probability, and you start counting, okay, which are the paths that contain the word to in the first position, and you add up those probabilities, and they add up to 0.5. Then you go to the next one and say, okay, well, how about the word in, and so on, right? So you start adding up all the probabilities, and you end up with some words there in the first position, and you keep doing that as you go, right? Second word, third word, and so on. And here at the end, they're not going to end up in the same bin. Some paths are shorter than others, so you keep having bins. But at some point, you are done. There's the diameter of this graph, and you're going to be done. That's going to be it, the longest path in the lattice. That's how many bins you're going to have here. And here we're going to use posterior probabilities for a word happening at a given position in my spoken document. So we would like to actually calculate this particular probability. The probability that word W happens at integer position n, greater than 0, less than diameter of the lattice, of course, because after that it's going to be 0. And I'm going to call this a soft hit. And if you remember what I was calling a hit in the text world, I was saving context in the form of word position in document, plus whether it's in title and so on. Well, here I'm just going to save the word position, and the title is going to come in some other way, right? So this is what I call a soft hit. And once you have this, if you think about it, you're not that far from actually taking all the probability, all the IR text world IR algorithms and applying them to the speech case. Instead of, before you used to count things, features, now you just take expectations using this probability distribution. And from then on, everything follows, really. We can take all the algorithms that are being used on text and just plug them in here. So you can evaluate proximity features, you have the position. You can do phrase search, are these two words next to each other? We're losing. This is an approximate representation of the original lattice because I now allow paths that were not there in the first place. So yeah, that's a bit of a problem. It didn't hurt us much, I think, although we don't have a formal evaluation for how much that is a problem. And if at all, it might actually improve recall. The other issue is that when we want to deal with out-of-vocabulary words, it's going to be hard to incorporate sub-word level information. Like if you have a phone lattice and you want to align it with this soft hit grid that I just showed you, well, there's no more time information there. Things are tricky, right? But that's for future work.
How much does the index grow when you have this?
There's going to be numbers. So,
Another quick question?
yes.
Whatever.
So the transformation from lattice to the bins, is it similar to what data calls confusion network?
It's very much in the same family of algorithms. I should have, I'm not sure I have a slide at the end, but if not, I should get to it somehow. Maybe it's better to go through it, and then I can explain the minor differences between the two. And I think that should work as well, if you try it. This was just a straightforward thing to do. I don't see why not do this. It's a little simpler, less hacky, and it should give more or less the same results, I think. Yeah.
So on the previous slide, where you described soft hit as being in a position N in the document,
Right.
Should we now interpret N as being a count of frames rather than a count of words, or do you still?
No, it's a count of words. N is a count of words from the beginning of the path in the lattice.
Why do you break things out that way?
Because I'd like to think of it as a string of words, because that's what people that do text retrieval do.
It's not clear to me why it's a good idea, since there may be some uncertainty about the number of words before the preceding word.
Yeah.
Which doesn't actually, it's not clear to me why that would actually be relevant to computing scores. you don't care about absolute offsets.
Well, let's say
care about
that you have a feature in your text retrieval algorithm that says is word I within 5 words of word J. How are you going to do it?
Well, you look for a path that has with word I and word J and 5 words in between, but you don't care about the absolute offset from the beginning of the document.
But where is that information in the inverted index?
Well, you can do it by frame offset. I mean,
No,
I
you
understand.
can't. You can't. You can think. I mean, you can sort of guess it.
You can guess it, or you can say for given spans, what's the expected number of words.
Right.
It seems like for words later in the document, measuring from the beginning of the document, your words toward the end are going to have a great deal of variance. So the probability of a soft hit at words 1,000, 1001, 1002, you'll be smeared all over that.
That is true. It happens, and I don't have the graph.
Seems like you can do better.
There's a paper in computer speech and language coming up, and that will have exactly that graph. I call it smearing.
Yeah.
It's how you take a given word and it actually gets split across many bins in position. So if you were to do time-based indexing, you would probably have only fewer bins, but you still have a few bins because you have links in the lattice that correspond to the same word that start and end at different times. So you would need to somehow bin those two. It's not straightforward how to do it on times. You probably want to quantize there too.
Well,
Start time and
we
end
can
time.
take this off.
Yeah, but definitely you can do it that way. I'm not saying that this is the only way. This is one way, and what is attractive to me in this particular way of doing is the fact that I have the integer position, which is what text retrieval algorithms know how to deal with. I would need to take all the other stuff and try to port it according to some hacks or some heuristics to the time-based position information that you would get, right? That is something that you still need to solve in the other approach. Right. So that's why I looked at this, but yeah. So this is all work I've done at Microsoft. We took 170 hours from MIT iCampus data. It was recorded in conditions just like this, wearing a lapel mic. And the great thing about it is that it's transcribed, all 170 hours of it. And I thank Jim Glass from MIT. And we took the Microsoft dictation acoustic model. This is something, it ships in Vista, I guess, so you can actually go and play with it. It has, I think, unless they changed it, it had about 110,000 words in the vocabulary, trained on a lot of newswire text, but you end up with a pretty small language model. As the guys were saying, the Windows people were saying, guys, we need some space for the operating system on the CD, so you can't ship too big of a language model or recognize it for that matter. So the language model was a little smaller than what you're used to dealing with. Then we took and decoded the first 20 lectures in the introduction to CS. I mean, it's all the 20 lectures in the introduction to CS class in the MIT corpus. And you can find the first lecture online, actually. If you go and search for it, Jim Glass made it available. You can actually play with it. And here are the statistics that you were asking me about. If you look at the speech, it's 2.5 gigs uncompressed. The trigram word lattices came to about 300 megabytes. If you take the soft hit index unpruned, which is something that you normally don't necessarily do, you can cut it by pruning to maybe 1/5 of it. But you still get very little overhead on you need the content. If the content is on the web, then you still need to keep only the index, that's true. So then you can probably prune it. And it's still a lot bigger than the transcription index, of course. You have a lot more entries per word, and it depends on how big your lattices are.
And you can control it, right, by deciding how aggressively you do it.
Yeah, I'm going to have a slide on that. It's just standard for me. I mean, there's nothing really that groundbreaking here. It's
So the Vista wasn't dumps lattices?
The Vista decoder?
Yeah.
No, this was a different decoder. It was the Anthropic decoder, which came with Julian Odell. You should know about that, right?
I'm just curious what goes into Vista.
Vista, it's highly optimized. No, it was different. I don't think you could get lattices. But it's a decoder and the results are the same, very much the same, depending on the models. It was nice to have this luxury of having 2 decoders, because then you could really see that it's about the models, really. What do I do for ranking? Well, it's very simple, and I try to make as much use of the position information. Although based on this whole track eval business, it's not clear that it's going to help us in evaluating. But qualitatively, the results are much better if you look at proximity information. So what we do is, if you look at the query as being a sequence of n words, you can form n unigrams out of it, you can form n-1 bigrams out of it, you can form n-2 trigrams out of it, and so on, and grow it to the highest order n-gram in the query length, right? So you have all these sequences of words at each order. And then if you fix a particular order, n here, so I'm going to calculate relevance scores at each given order. And the relevance score at some order is going to just be the expected count of all the unigrams at that order in my document. And I just have this simple logarithmic scheme to taper off really high counts, because people found out that that's a good thing to do. So it's a lot of hand waving. The expectation is rigorous according to the soft hit distribution, but after that, it's really sort of out of the hat. And what we have is a linear scheme for combining different n-gram orders, because I feel that if you get a bigram hit, object-oriented, it's much more valuable than an individual hit for object and another one for oriented. And as the order goes up, the bigger the bonus for hitting that n-gram, right? So if somehow you enter weapons of mass destruction and you get the whole thing, well, you're going to like the document. So I should show it first, and then go down the back of scheme there. So very simple. Again, the evaluation framework was that of trying to bridge the performance between speech and text. And I did what we discussed. Took a TF-IDF engine, ran it on transcript. The little mismatch you see here between our result and the baseline, I used technology that was Microsoft. I wanted to make sure my implementation was right. And that's because of some text normalization issues that they were doing, and I couldn't get around them. So there's a small mismatch there, but really, basically, we have it right. If I run our engine using one best transcripts, I mean, you can create that little lattice that we discussed, the soft hit lattice, using just one word per bin, and the confidence, the posterior probability ought to be 1 because you have no other choices in a given bin. So the one best can be represented as a soft hit lattice. You get about 0.53 mean average precision, and when you start using the lattices, you get a pretty big improvement, 70%. And as I was saying, this was done on 116 queries, and we saw here a 5% out of vocabulary rate. So I was wrong when I said 10%. It's 5% out of vocabulary rate on the query side. We have 2 words per query, so basically we're looking at about 10% queries that have 1 word out of vocabulary. Still high. We're not dealing with that though. So those queries were thrown away, right? In this evaluation, we're only in vocabulary query. So the other more interesting thing was, okay, I said, all this position information is not really shining because the reference was just simply counting the documents which had that word or didn't have that word. There was no position information in the reference, really. So I think that I would see a lot better what the virtues of doing, soft hits and indexing position and all that if I looked at some quoted queries, right? So now I went through my query list and I quoted reasonably the meaning of the query, right? So whether you accept it or not, I think when you query for object-oriented programming, you sort of have in mind this parse for the query. I'm talking about object-oriented, and it's some kind of programming. When I talk about speech recognition technology, well, it's more or less it's a phrase. It means something, and I would like this, right? So you probably noticed that Google does this too. I don't know if you did, but there's quite a bit of work behind the scenes on interpreting the query. And one reason that we're good is because we do that well. And Well, here's the first step towards it in this particular framework, and it was done before I got to Google, so it has no connection whatsoever with what Google does, okay? So, then if you take the one best and you look at the mean average precision there, we can't use TF-IDF is irrelevant at this point. I'm just using our own engine running on one best, but I run these queries, and I enforce the fact that the document should contain this phrase exactly like this. That's a hit. Nothing else is. If I have objective programming oriented, that will not be a hit for this query, right? It won't come up in this relevance ranking. So again, output reference on transcription, but again, hits are only those that match exact the phrases. When you look at one best, you get 0.6, 0.58. If you look at lattices, big improvement, 26%, right? And you can guess why that would happen. Here is the PSPL lattice, the soft hit lattice, and you have position 30, position 31, and 32. And what the speaker said was anti-ballistic missile treaty. And you can see the alternatives here, and I just took the top ones. And if you search for anti-ballistic missile treaty as a phrase, you're going to miss it in the one best output, right? It's not there. Ballistic missile treaty, that's what the one best reads. And if you allow the alternates in the bins, you're dramatically improving your recall. That's basically what happens. And the interesting thing is that you're not doing that at an equal cost in precision, because if you look at all the other combinations that you could make there, not many of them make sense. And I think my explanation for it is that we're entering queries that are sort of frequent n-grams, which means that they're likely to be encountered that way in a document, that they're a typical n-gram.
This is not the lattice, that's the sausage, right?
It's the, sausage, yeah. Position, posterior.
Yeah. So in other words, these are not paths, actually. There could be no path anti-ballistic missile treaty, actually.
Correct.
Right.
No, actually, it's worse than that, because maybe the person said missile anti-ballistic treaty, but because these are indexed by word position, there was some reasonable probability that missile was at word 31.
Yeah, in fact,
I'm sorry, missile was at word 31.
You get
word 30, even though they were actually pronounced in the other order because of the smearing effect.
You get treaty and missile for the swap here.
Right.
So if you
because you're making an independence assumption about the soft hit indices, right?
And the numbers you have here are the log likelihood?
Log probabilities. These are posterior probabilities in log space.
Yeah.
So you're right. So if I was to search for a treaty missile, doesn't mean much. But if you were to search for a treaty missile, you would get a false hit here. But I think that's why we actually gain, because you never search for a treaty missile. It's not something that means anything, right? So I think that gets to the core of this, really. The fact that you're searching for typical n-grams. Otherwise, you might get swamped by the loss in precision. So coming back to pruning, yeah, you can prune the index. You get a curve like this. You have pretty good recall, 85% recall at only 30% precision, and you can actually travel all the way to 90% precision with very low recall. So you can do it. I mean, if you really want a specific search, I want to really know when somebody mentioned the president's name, right? Well, I can find all those documents. I just need to put up with about 90% precision. 30% precision, right? So that means that I will read 3 times more than I should, or listen to 3 times more than I should. But I will only miss 15%. And you get the other end of the spectrum. You can't do that on one best. On one best, you're here. Done. Another interesting thing that I would like to cover before I finish is text metadata, right? Everybody's like, oh, but this is only speech, right? We have text, and why do we need to do all this speech? Because I have the title, I have the abstract, and I have biography for the speaker and so on. So why can't I just use that? I index that, and I search strictly using that, and I should be good, no? And the evaluation doesn't change, at least for this slide. And we're only looking, assuming the reference assumes that I have the transcription, and then when I build my index, I only index the text metadata that I have for the lectures, which ends up, we counted, and it's less than 1% of the transcription. So that's very important, because that's roughly the ratio in size that we're looking at. Speech content, number of words in speech content versus number of words in speech transcription. It's expensive to transcribe speech. People write short abstracts, it's an abstract. So because of that, when we look into the speech content, even at 40% error rate, which is what we have here on the MIT iCampus data, you gain a lot. We have a 300% relative improvement and mean average precision by using speech. And then, things get worse a little bit as you weigh things towards the speech side only. But really, the big gain is simply, let's use speech over text. And these are the precision recall numbers. If, when you just use the text metadata, very high precision, extremely low recall. You just don't get all of them. Very few of them. If you just use speech, well, 8, 3, the upper left corner that we saw there. And by combining them, you don't gain much, but still. And I'm going to skip that slide, and that's the summary slide. I'm arguing that tighter integration between black boxes such as speech recognition and TF-IDF, or I don't know, if you do speech-to-speech translation, it's a really bad idea to just take the one best word sequence, especially if you look at domains which are outside of what you train. You lose any handle on the variance there. What happened? How much of a hit in performance am I taking? Is my system robustly dealing with that? And I think lattices are a promising way in that direction. And I've heard there's work on that here, right? So I think before moving forward in this space, it would be good to establish another evaluation metric, which actually takes into account the ranking on the text side as well. Because right now we're just looking at a set of documents and how quickly do I get documents in that set. I'm completely ignoring the ranking there. So I think that should be done. And finally, there's a lot to be gained from integrating other streams of information if you have them. And that pretty much concludes my talk. There's a demo that I won't have time for, but you can go and play with it. It's at the MIT website under Galaxy CSAIO MIT EDU/lectures. And they use TF-IDF ranking here. There's nothing that involves proximity or anything like that. So I know I could try a query now. If we have time, I can take questions. We're running a bit late here.
Let's see if there are any questions.
I just have a comment that there is a company called Nexidia which does retrieval just the way you talk, but they do a phonetic recognition and index that.
Great.
If you had any opinions about that.
Well, I played with a system like that. Frank Zaide in MSR in Asia, Beijing more specifically, built a system like that. And so, two comments. One is the inverted index is unclear. It becomes pretty big when you index phones. You can't actually index phones because you will have each phone happening in pretty much every document. So you don't gain anything by doing that. You need to index larger units. And as soon as you go to phone engrams, your index will blow up. So what he didn't have an inverted index. He had the lattices, and he had the way to prune the search space using some language modeling techniques. He was building a language model. He was never able to scale to 200 hours of data using that system. Well, he did, but it was taking a long time to do the search. So there's core engineering scaling up issues with that. The other problem with it, which is on the retrieval quality side, is the following. When you do phone recognition, you lose the word boundary information. And that is a big problem as far as we're concerned here, because we think in terms of words, and for example, I was playing with this system, and you would enter, what was the query? You would get a hit for Asia in information. And you can see how that might happen, right? There's no real good way of dealing with that. You can't really put the word boundary in the phone recognizer. You need a word recognizer for that, right? And so I think that's why traditionally people haven't liked that, because you probably see very good recall. I mean, you get all sort of stuff, but the precision is pretty poor. And so there's these two comments that I would make about such a system.
If anyone's tried syllables and stress patterns?
Syllables and stress patterns, and that would be for building a better acoustic model when you do the recognition, or?
No, instead of a phone model where you have just phones using something like syllables and stress patterns to deal with out of vocabulary issues.
So I see. So basically, use a subword recognizer, and instead of using phones, you use some more sophisticated. No, not that I know of. I haven't worked much in that space myself. People that have tell me that the best way of generating phone lattices is still by running a word recognizer and then converting that back to phones, because that constrains the space quite a bit. And if you think in terms of indexing, it's a little ridiculous, right? What would you do? You would take a word recognizer, run it, get a word lattice, use some finite state machine that you have there to generate, the inverted lexicon, to generate the phone lattice, index that, and then get the words and try to match them against that. So to me, that sounds a little roundabout, and I think a good research direction there is to somehow do the matching between the word and the word index directly. Even though the word is OV, well, if it's OV, you take the query word, match it to phones, then back into words, and then do the search that way. Because really, you're doing the same thing. And the computational overhead is not worth it to store phone indexes and so on.
I agree with your comment, but their marketing pitch is that since phone recognition can be much faster, and I assume they are doing one-best recognition, and it can be much faster, and then they can use some kind of fuzzy match on the spoken terms, so they have a very good recall, except that the precision is low.
I mean, if you want really good recall, you just return all the documents, right? And you're done. So, people.
You still have to decide in what order you want to return.
I keep joking about it, but I can build a speech recognizer right now. If I had the Perl console, I can just echo "Hello World," and I would ask Fred to say something, and he would not say "Hello World" for a while, and then after a while, maybe he's going to say "Hello World," and that's a speech recognizer. It's just a really bad one, but that's how you have to think about them. It's you're guessing, and you're using a statistical guess.
I think you have to wait a long time.
But I'm
I say
excited.
hello world.
So I'm of course exaggerating here, but I'm trying to get a point across, right? You can't just look. It's a statistical thing, right? Anyway. Okay, so thank you. You can play with it.
I thought you were going to show us Jim Glass or something.
Right. So this is the demo, and
So let's thank Ciprian first, and let's play the demo.
We don't need this.
so unfortunately, I don't have. Somehow I don't have.
Oh, there you go. Yeah, the mouse is back.
So
You want this quick? Ah, there you go.
so you can enter voice query. And it's unclear that really this is very good, this ranking, because
So you're going over the network.
Weapons attempts to control the weather and the color white.
so there was a hit for weapons.
Now, evolutionary psychology mass quantities of the stuff. Our tastes have not caught up, and we therefore eat more of them that are good for us. Everything from aesthetics.
Yeah, sorry, the connection doesn't keep up here. But it doesn't seem really that this document is relevant to anything that has to do with weapons of mass destruction. And I think the problem here is exactly the proximity issue that we were talking about. The transcription quality is not that bad.
But the second document might be.
The second is probably, yeah. I know for sure that.
When I first wrote my first column, the editor said, "Where's the edge?" I said, "The what?" "Your opinion." "My what?" After 50 years of censoring myself. Anyway, it's fun. What?
Well, so I think this is indeed relevant. The browsing question is quite pressing here. How am I going to find the segments that really are about weapons of mass destruction? And you can see how this is not doing very well.
So it matched weapons of mass destruction with nuclear weapons, which is the same, which is very relevant, of course.
Well, no. So the whole document is listed here, right? So you only see the hits in this particular segment.
Right, but then
if I go here, this should also have some relevant. So there's mass here, and there was no destruction.
Weapons of production. Oh, but is this one best?
This is on the one best.
Yeah.
I don't really know if they return strictly only documents containing all the hits, all the query words or not. Yeah, we need to ask you. So, but you know, it's sort of a prototype for how something like this might work.
This is done your way.
No, none of what I talked about is in here.
So this does not. So I'm sorry. I guess I missed it. So what is the method by which this does its work?
They do speech recognition using the MIT system. I don't know what exactly is in there.
And they do one best.
They have one best speech recognition output, and
And then
they
so
feed it
this is a demonstration why what other people do is no good.
It's really no. It's very good.
What do you mean it's very good?
Well, I mean, think of not having it. Okay.
I didn't
Because
have
that's
it
where-
until this
that's where-
very second, and I was quite happy.
Right, well, you see, yeah. I guess we're too young.
Okay, well, why don't we thank you again?
Yeah.